Hello everyone, my name is Luo. Today I'm going to talk about KungFu, a library that can make training in distributed machine learning adaptive. This is a joint work with Guo, Marcel, Konstantinos, Andrei, and Peter from Imperial College London. Today, AI developers are using distributed training systems such as Horo and TensorFlow to scale out the training of their models. These systems, they usually implement data parallel training. They partition the dataset and then replicate the model on all the worker machines. To use parallel processors such as GPUs, they compile the models into the data flow. In every iteration of training, the data flow will read the data batch and compute the gradients. The gradients need to be averaged across all the worker machines. And this is usually achieved using or reduce provided by collective communication systems. The training needs to last for many iterations until the model can reach high accuracy. In using the systems, the user must tune many parameters to optimize the time to accuracy performance. They often need to tune the hyperparameters, such as the batch size and the learning rate. These parameters define how the model is being updated, and they decide the model accuracy. Users also need to tune system parameters such as the number of workers and the communication topologies. These parameters decide how the workload is being distributed across the worker machines, and they affect the training throughput of the system. In tuning these parameters, users often rely on their empirical experience. In training with ImageNet, for example, users often change the batch size at certain data epochs. And this static schedule of batch size is only applicable to ImageNet when the user are moving to other datasets. It needs to be retuned. When the user are training the ResNet models, they often linearly scale the learning rate with the number of workers. This linear scaling rule often works well for the ResNet models, and it barely works in other models such as BERT. If we look into system parameters, existing collective communication systems often fix the choice for collective topology to the ring by default. The ring topology can work well in an HPC cluster. However, in a cloud cluster where the network bandwidth is limited, the ring topology often performs poorly. To avoid the issues of empirical parameter tuning, people are exploring automatic parameter adaptation. A recent proposal is from OpenAI. OpenAI tried to automatically set the batch size based on monitoring matrix called gradient noise scale. Intuitively, the gradient noise scale can measure the variation in data batches. When the noise scale is small, that means the system cannot learn from the many data samples in parallel, and the many data samples becomes redundant, and there's no need to further increase the batch size. When the noise scale is large, that means the system can effectively learn from the huge batches of data, and this is a good signal to further increase the batch size to help the system to converge faster. We are observing many similar proposals recently. So for example, Apple and NVIDIA are monitoring gradient variance and the gradient second order matrix to automatically set the learning rate. People are also monitoring worker performance metrics to decide the optimal number of workers. In all this proposal, we can see a common pattern. People are creating control loop to monitor the training workers, and they are using monitor metrics to make online adaptation decisions. We want to design a distributed ML system that can support adaptation. And this system should support different types of adaptation because the adaptation often rely on analyzing the monitoring data, such as gradients. But however, modern deep learning server can produce several gigabytes of gradients per second. And this is challenging to analyze the gradients in the real time. And the training worker usually have very large training states, such as the model. When we are adapting their parameters, we must ensure the adaptation would not affect the consistency of the state on distributed nodes. Otherwise, the training results will be compromised. But how does existing systems support adaptation? TensorFlow and the Overview, they don't have unified mechanisms for adaptation. Their users often implement custom and external adaptation frameworks. And these frameworks don't have generic API to support different types of new adaptation proposals. And their training worker will dump monitoring data as logs through external libraries such as TensorBoard and MLflow. This library processes monitoring data offline, and there's no natural way to send the results back to the training system to make online adaptation decision. These libraries are also not designed for analyzing tremendous gradients in the real time. To protect the consistency of the state, the training worker often requires the user to checkpoint their state and do the recovery under adaptation. And there are many steps will be involved in this checkpoint and the recovery process, and this will build up large adaptation latency. In this talk, we will introduce KungFu, a new library that will make adaptive training easy and efficient. The first contribution of KungFu is the design of high-level adaptation policies. These policies have APIs that are intuitive for the machine learning developer. They are being implemented using API functions that can be used to monitor and adapt existing TensorFlow, Pietzuch, and Keras workers. And we show that this function can be flexibly combined to implement different types of adaptation. To ensure the policy can be efficiently executed during training, KungFu proposed to embed monitoring operator inside the data flow. And this allows KungFu to process a large volume of monitoring data during training. To support online adaptation towards parameters, KungFu has new distributed mechanisms. And this mechanism allows the KungFu worker to expose low-level system parameters in a safe manner. And when the parameters are being changed, KungFu can automatically synchronize the updates and make sure the adaptation is consistent. We are discussing how we design the adaptation policies. The ultimate goal here is that we want to enable the user to express complex adaptation over control loop for parameters. In the KungFu, we replicate the policies on all the workers, and the policy will monitor the data flow in parallel. To aggregate local monitoring result, they will use the communication functions. And when the policy agree on one decision, they will apply adaptation in parallel. To help a user write many such policies, KungFu provides expressive API functions, such as those for doing different kinds of monitoring, different kinds of communication, and adapting different parameters. We show how a KungFu policy works using the gradient noise scale example. In this sample policy, the user wants to monitor the gradient noise scale to adapt the batch size in between every training step. The user will embed user-defined adaptation logic inside the policy by overwriting their policy function called after-step. And inside this function, the users will call gradient noise scale function to collect monitoring results. It will call or reduce to combine the local monitoring results. And if the noise scale is growing, it will call the reset function to increase the number of workers. KungFu further provides an optimizer that the user can be used to wrap the local SGD optimizer. And the KungFu optimizer automatically embed monitoring inside each training step. KungFu further provides a hook object. The hook object can wrap all the KungFu policies. It can be passed to a high-level model trainer such as TensorFlow estimator and automatically schedule the execution of the policy in a transparent manner. And this makes sure the KungFu policy will have minimal modification to existing machine learning programs. KungFu embeds monitoring inside the data flow. And the major reason is because if we are having many adaptation policies, we want to ensure they won't cause large monitoring overheads, which will reduce their adaptation benefits. And our idea is to improve monitoring efficiency by adding monitoring operator inside the data flow graph. We show how this is achieved using this sample data flow graph here. We want to do gradient noise scale monitoring, and the KungFu will append this operator to gradient operators. And to combine local noise scale metrics, KungFu will further append or reduce operators. These embedding designs allow monitoring to take advantages of Dataflow engine, which has been optimized for using GPU and parallel execution. It also allows monitoring to use collective communication, which can scale out the distributed monitoring of gradients. But by calling a lot of collective communication inside the data flow can create problems. Modern data flow engine launch operator asynchronously. This can be good for GPU and CPU operators, but it becomes problematic for all reduce. Collective communication systems such as MPI require the user to synchronously call the or reduce. That means at any given time in the entire system, you can run only one single or reduce operation. If you have multiple or reduce is being available asynchronously, that means the user must use a central coordinator to coordinate their global execution so that they can be run one by one. And this coordinator often prevents the system from scaling. To address this issue, KungFu want to enable asynchronous collective communication. And the key idea is as follows. As long as an or reduce operator is ready, it will immediately send the or reduce message to its downstream workers without waiting. The message will carry a key and a data. By reading the key, the receiver will know if it has seen the data belonging to this key before. If not, it will create an intermediate state. The state has a control field which can tell the progress of the accumulation. If the accumulation finish, it will create another message will pass the results to its downstream workers. As we can see in asynchronous collective communication, there's no need to do global coordination. KungFu has distributed a mechanism for supporting online parameter adaptation. And the problem here is that existing training worker, when they are doing adaptation, they could affect the consistency of the state. And we show this issue by using this sample data flow graph. Assuming that we want to compute the average value of the gradient noise scale. And we are compiling the current value of the number of workers, like 10 here, inside the data flow. And then later, when we want to update the value, that means we need to recompile the data flow. And this is the major reason why adapting system parameters often require the system to restart, because we coupled the system parameters and the data flow. And we can see similar problems in other system parameters. And our idea, therefore, is to decouple system parameters with the data flow state. And the way we achieve that is that we represent system parameters as computational operators. For example, the number of workers is represented as a size operator. And the value of this operator is lazily decided by reading from the worker membership table inside the KungFu communication layer. Later on, when the user wants to update the size, it will use the parallel updates. The KungFu communication layer will use collective communication to check the consistency of these parallel updates. It will further enforce a global adaptation barrier to ensure all the membership are having consistent state before moving into the next training step. And by doing this, KungFu can support online parameter adaptation in a consistent and fast manner. We evaluate KungFu using testbed experiments. And we compare the gradient noise scale policy to other empirical setting in choosing the batch size to show that the benefit of enabling adaptation. Users in this state are often using small batch size to train their models. And a small batch is very good to reach high training accuracy, but it underutilizes the hardware. It takes very long time to finish the training. If we switch to the large batch, we can quickly finish the training. But however, the large batch also reduces the number of training iterations. This makes the model often end up with a bad minimas, and the model accuracy suffers. And in KungFu, we are using gradient noise scale to guide the setting of batch size. As we can see from this figure, KungFu suggests the user to use small batch in the beginning of training and then later increase it until the later stage of training. And this has very good benefits for the model accuracy. And the KungFu achieved the best time to accuracy in these experiments. And also we can see by enabling online adaptation, KungFu can still finish the training very fast. And this is mainly contributed to the embedded monitoring and the online adaptation design in the KungFu workers. We also compare KungFu's distributed performance with the state-of-the-art HoroVolt. We run the experiments in the cloud with 32 virtual machines, and each machine has 1 GPU. When we are training the resonant model using 32 machines, we can see KungFu achieves 50% higher throughput than HoroVolt. And this is mainly because the asynchronous collective communication avoid global coordination, and this allows KungFu to scale better. In this talk, I introduced KungFu, a new library that can make training of machine learning models adaptive. KungFu is inspired by the proposal from automatic parameter adaptation recently, and this proposal are difficult to be implemented using current system because they have no unified mechanism for adaptation. And the KungFu filling the gap by providing adaptation policies. To optimize the efficiency of running these policies, KungFu embed monitoring inside the data flow. And the KungFu further provide distributed mechanism to support consistent parameter adaptation. KungFu is open source on GitHub, and you are welcome to download it and start playing. Thank you.